Okay. I start?
I will introduce you first.
Yes, sorry.
Hi everybody. Our next speaker is Youcef Mokrani. He will talk about generalization of Monsky matrices for elliptic curves in Legendre forms.
Thank you for the introductions. Today I'll be presenting the results of my master's thesis at University of Montreal under the supervision of Mathilde Vlanet. Since we have a lot of things to see and not much time, we'll just start right now. We start with the base example. Positive integer n is said to be congruent if there exists a right triangle of area n whose sides are all rational length. Super quick, we can just suppose that n is square free because we can just multiply every side by alpha to get alpha square n. So n is square free for the rest of the talk. And one of the very basic interesting facts about the congruent number problem is its link with elliptic curves. So if E is just this elliptic curve, then so y squared equals x cubed minus n squared x. And a positive square free integer n is congruent if and only if this elliptic curve in the rationals has a positive rank. There's a lot of results that come from this. Probably the strongest will be tunnels that I'm grossly paraphrasing here, but basically there's an effective way that is known to check if a number is congruent if and only if the BSD is true. Sadly, we don't know for sure that BSD is true, so we'll try to find ways around it. Anyways, so the first thing we can remark is that we can just factorize the elliptic curve in order to be x minus n, x plus n. And then in general, that we say that an elliptic curve is in Legendre form if it can be written as x minus e1, x minus e2, x minus e3, with e1, e2, e3 being rational and distinct. Basically, it has a Legendre form if its two torsion is completely irrational. So, and without losing any generality, we can reduce it to be in this form with e2, e3 being distinct integers, their GCD being square free, and the two valuation of E2 being bigger than the two valuation of E3. So for the rest of this talk, the methods that we will show apply to any possible elliptic curve in this form. However, because of time constraints, the application will only be done in the classic case of congruent numbers. Anyways, let's start. So we want to find the rank of the elliptic curves from model Y, etc. We know, since we know that the two torsion is full, we know that the elliptic curve group is isomorphic to Z2Z times Z over 2 NZ, not the same N, times Z to the rank. So if we just quotient by 2E, we get that E over 2E is just Z over 2Z to the rank plus 2. Which means that now we can just try to study E over 2E. And to do that, we just need some definitions. The discriminant of an elliptic curve in Legendre form is just 16 E2 square, E3 square, E3 minus E2 square, just classic formula. And for any integer, let's say delta, because that's why we'll use it, we say that K delta 2 is just the rationals quotiented by their square, such that for any prime not dividing delta, the valuation of B and P is even, aka we can just see it as K delta 2 is the set of every square free divider of delta. Anyways, there's this theorem. I'm not certain exactly where it was first introduced, but it can be found as an example in theorem. Anyways, if E is an elliptic curve in a reduced Legendre form with discriminant delta, then there is a group monomorphism from E over 2E to K delta 2 times K delta 2, such that for any pair B1, B2 has a pre-image if and only if this equation system has a rational solution. So we went from congruent number to elliptic curves to just finding this possible B1, B2, since for which this has a solution. So super quick corollary, then if R is the rank of the elliptic curve E, and H is just the set of pairs B1, B2 such that the previous equation system has a solution. Then clearly R is just logarithm base 2 of size of H minus 2. So now there are so super quick theorem that if we go back to the congruent numbers, N is congruent if and only if there is at most 4 pair B1, B2 such that the equation system has a solution. We can just multiply, since we search a rational solution, we can multiply everywhere by the denominator, the common denominator of Z1, Z2, Z3 to get this equation system with Z1, Z2, Z3, D all integers, D not equal to 0, and the GCD of Z1, Z2, Z3, and D being equal to 1. And also we can, instead of looking at congruent numbers, we'll be looking at non-congruent numbers. So if and only if at most 4 pair B1, B2 have are such there is an integer solution here. Okay, so since we, since we are only looking at, we just want that at most 4 solutions have a solution, at most 4 pair have a solution, we'll just try to find necessary conditions in order for a solution to possibly exist. So we'll just look at the local domains. So we know that an equation system has an integer solution only if it possesses a real solution as well as a solution in Z modulo mz for any integer m. So if instead of, if H prime is just the B1, B2, such there is a solution in any local domain, then clearly R is smaller or equal to log base 2 of H, the size of H prime minus 2. Basically, we're just studying the two-cell group of the elliptic curve. So now we just want to find enough conditions to prove that there is at most 4 pair B1, B2 that have a solutions. So we'll just find conditions for every single local domain. In the end, we'll find 1 condition on R, 2 condition for any prime odd primes dividing delta. We'll be finding 2 conditions in ZP, and 3 conditions in Z2 for 3 conditions in Z2. Why there is 1 condition here, 2 conditions here, 3 conditions here, is that it can be shown that those conditions are sufficient for a solution in the given domain. So at the end, the matrix we will show has is isomorphic to the Selmer group. Anyways, so there are a lot of conditions. So instead of showing every single condition, we'll just show an example for every domain. The most simple will be in R. In R, we have this equation system. The third equation is just the second minus the first. Anyways, so if E2 is negative and E3 minus E2 is strictly positive, one of the conditions is that for a real solution, B2 needs to be greater than 0. The proof is very simple. For just a case-by-case proof, if B1 greater than 0, B2 smaller than 0, then this is positive, this is positive, this is negative, this is a contradiction. And if both are smaller than 0, there's the same reasoning with the third equation. So we have found one condition on R. We can do the same for every possible E2, E3, and find other conditions. For the condition in ZP, there is 1 condition on B1, there is 1 condition on B2. We'll just do a condition on B1. So for example, if P divides exactly E2, E3, and E3 minus E2, there is 1 condition depending on if P divides or not B1 and B2. So for example, if P doesn't divide either, we have that B1 needs to be a square modulo P. So how do we show that? We still have our equation system. So we just, we suppose there is a solution. So if P divides Z2, then P divides Z2, then so this is 0 mod P, this is 0 mod P, this needs to be 0 mod P, so P needs to divide Z3. So since P divides Z3 and Z2, this is 0 mod P square, 0 mod P square. This is exactly divided by P, so the P also needs to divide D. Then since we know that P divides D, we go back to the first equation. P needs to divide, P squared divides this, P squared divides that. So automatically P needs to divide B1 Z1 square, but P does not divide B1, so P divides Z1. But remember, we said in the solution that the GCD of Z1, Z2, Z3, and D cannot be other than 1, which means that we have a contradiction. Therefore, P does not divide Z2, Z3. Because P does not divide Z2, Z3, we can go back to the third equation and just look modulo P. So this is 0 mod P. So we have just this equation. We also isolate B1. So B1 is just congruent to a square mod P. So B1 is a square mod P. We can do that for every single case, and then we do that for every single possible evaluation of E2, E3, and E3 minus E2. It's very long, but it's doable. And then an example of condition in Z2. Z2 is probably the most complicated for the conditions because just Q2 has a lot that Q2 acts very differently for two odd primes. Anyways, so for example, one of the possible conditions will be that if 2 do not, when 4 divides exactly E1 and 2 divide exactly E3, if 2 doesn't divide either, B1, B2 needs to be congruent to 1 mod 4. There are other conditions that ask, for example, that a term is congruent to 1 or 3 or 1 or 7. The good news with that is even though the conditions are complicated, the proof is not. We can just do, for example, brute force modulo 32. We can prove that this condition for the 3 conditions we find are sufficient by doing an induction on, since studying Z2 is just sort of studying Z over 2 to the KZ, we can just do an induction modulo K, an induction on K, sorry. Anyway, so now suppose that we have found every single condition. What we can do, we want to create a matrix that represents every single condition. To do that, we start by seeing n in our congruent number as being factorized as 2 to the delta times our disjunct primes, since it's square free. Then since B1 and B2 are in K delta 2, we can see B1 as being minus 1 to the epsilon 1, 2 to the delta 1, and a product of the primes dividing n to the alpha I. And since B1 and B2 are in Q over Q squared, then we can see all the exponents here as being in Z over 2Z. Because of that, we can just represent the pair B1, B2 by the vector of the exponents. And then the goal will be, we'll just try to find a matrix whose kernel is exactly the pairs B1, B2 respecting every single condition. In order to do that, we just, for every single condition, we find a vector Y such that Yx is equal to 0 if and only if X represents the condition. And then we can just stack the Y's on top of each other to get the desired generalized Monsky matrix. So how do we get the lines? For example, we remember that our first condition is that B2 needs to be greater than 0. This simply is represented by taking the vector 0 everywhere except the column representing the exponent epsilon 2. Epsilon 2 is just here, is just the exponent of the minus 1 of B2, which means that Yx is just equal to epsilon 2. And this is 0 if and only if B2 is positive. It respects our condition. Same thing we can do for this complicated condition. This time, instead of looking at the valuation, we can just look at Y being 0 if the column represents a square mod P, or 1 if it doesn't, if it represents not a square mod P. And then when we do Y times X, it just gives us the Legendre symbol. It gives us 0 if this Legendre symbol is 1, and it gives us 1 if it's minus 1. This is exactly what we wanted. And then we can do something very similar for in Z2, this time just taking 0 if it's 1 mod 4, and 1 if it's minus 1 mod 4. And we can just get our matrix lines. So now that we have our matrix line, let's call, for example, let's go back to the congruent number problem. Every single result I'll be saying right now can be generalized to every single elliptic curve. Anyways, so let n be a square free integer and mn its Monsky matrix. Then if the dimension of the kernel is smaller or equal to 2, n is non-congruent simply because the size of the kernel is just 2 to the dimension of the kernel, which means that if I generate the Monsky matrix, since it's square, if all but 2 matrix lines are linearly independent, then the kernel is of maximum size 2, and then n will be non-congruent. So it calls for the definitions that n is SNC if the kernel of Mn is of dimension 2. So n is SNC, you can see it if the 2-Selmer group is trivial. Okay, so just quick example. We can show very quickly, for example, that 11 is non-congruent by generating the matrix, taking off 2 lines, and then just showing that the rest of the lines are linearly independent. But what's really interesting is that we can prove some way more complicated theorems. What we call induction theorems is that, for example, if n is an integer and pq are distinct odd primes not dividing n, if p and q are congruent to 1, if n is congruent to the same thing, if n is not a square either mod p or q, and if pq is if p is a square mod q, if I add the conditions that every prime dividing n is either a square in both or not a square in both p and q, then we have that the kernel of the matrix of Mn is the same that of the same size that MPQN. So first result we get from that is that if n is SNC, MPQN is SNC, and then once we find a SNC number, we can just find an infinite family of SNC numbers. So how do we prove that? Mn is just this matrix. We have no idea what's this matrix. However, when we do PQN, multiplying PQ to n can be seen as adding 4 columns and 4 lines. And because of our conditions, this subline and this subline are the same, this subline and this subline are the same, this subcolumn is the same as this one, etc., etc. And because of that, if I add this column to this column, it gives us a lot of zeros, 1, 1, a lot of zeros. Because of that, I can just add this line to every line I want in C1, every line I want in C2 to just delete them. And then we can do the same thing with the 2 last line to delete C2 and C4. And because of that, well, this line is completely linearly independent. This means that if I take out this line and this column, I do not change the kernel size. I can do the same with those 2, and then I can do the same with those 4. And then I deleted the additional lines and columns of the MPQN without changing the kernel size, which completes the proof. We can do something very, very similar for when P and Q are congruent and 1 or 5 mod 7, mod 8, I mean. Same thing when P and Q are congruent to 3 mod 8. It doesn't work on 7 in the congruent case, just because of the Legendre symbol of 2 mod P when P is congruent to 7. So we'll just complete this presentation with one final theorem, is that for any integer n, there is a non-trivial non-congruent multiple. What we mean by that is just, if n is square free, I can find a square free multiple of n that is non-congruent, guaranteed, even if n is congruent. I don't know if this result is completely new, but I'm guaranteed that. But it's a cool proof. By construction, how we do that is first we start by factorizing n, 2 to the sum 1 or 0 or 1, 3 to 0 or 1, and then we separate every other primes depending on their congruence mod 8. And once we do that, since we have our 3 theorems above that that work in pair of primes mod 1, primes 1 mod 8, primes 3 mod 8, and primes 5 mod 8, we can just add one. We can just find a prime that respects the condition we want, And then the Q1J, we'll explain them later. But because we have all the condition we wanted, then M is SNC if and only if this thing is SNC by deleting the primes mod 1 mod 8. We delete the primes 3 mod 8, we delete the primes 5 mod 8, and then M is SNC if and only if this is SNC. We don't have we don't have a general theorem for that, but we can just calculate the Monsky matrix of this number that is the final number. We can choose those conditions, no problem. And then how do we prove that this is SNC? Well, this is the form of the Monsky matrix of it. It seems complicated, but it's the same that, it works the same that when we worked with 11. We just take out 2 lines we don't want. We find out that this line is linearly independent. We find out that those lines are linearly independent. We find out that those lines are linearly independent, and we continue until there are no more dependent line. And we just showed that for any number there is a multiple that is non-congruent. And with this empty matrix, I complete my presentation. Thank you.
Thank you.